BC Chemistry, Unit 4. Now let's talk about carbs. Okay. What are actually carbs? Well, they're mainly composed of hydrogen, carbon, and oxygen. And they all have a general formula that is a carbon with a bunch of water together. So you notice that the hydrogen to oxygen ratio is always 2 to 1, like in the water format. So compared to a fat and oil, it's a really high oxygen content. Carbs can be classified into groups based on structure. They can be monosaccharides, disaccharides, and polysaccharides. Saccharide is just a fancy word for sugar. So now you know that why people say if you want to thin down, don't eat carbs, because carbs are essentially just sugar molecules coming together to make bigger molecules. So like monosaccharides come together to become polysaccharides. So when they break it down, it becomes sugar again. So if you want to get thin, don't eat sugar, which is carbohydrates. Not that zero carbohydrates. Zero carb diet is a good diet. So remember this fundamental reaction that sustains life on Earth. That is the carbon dioxide and water coming together under sunlight, it becomes glucose. So do you think this reaction is endothermic or exothermic? Well, it should be endothermic because it's converting the energy of the sun to be stored in glucose molecule, right? So all these saccharides, they are very good at storing energy. Okay. So monosaccharides, they all have a chemical formula of C6H12O6. So basically, they are all isomers of each other. And also notice that the name is glucose, galactose, and fructose. So OSE ending, meaning that they are actually sugar. So we said that saccharide is a fancy word for sugar. So monosaccharide means that just one molecule of sugar. So they're the monomers. Notice that glucose and galactose only differ by position of one hydroxyl group. That is here. That is the fourth carbon on this entire ring. Okay, so we start numbering from the first carbon that doesn't have a chain next to the oxygen. So 1, 2, 3, 4. So they differ by the hydroxyl group position on the fourth carbon. And all of these carbons, you notice, because they are actually connected to 4 different groups, every single carbon on the ring. So how many chiral centers do you think glucose and galactose each have? So 1, 2, 3, 4, 5. As long as the carbon is in the ring, and they are chiral carbons because they are connected to 4 different groups. Therefore, there are 5 chiral carbons for each of the molecule. All 3 monosaccharides contain a number of polar hydroxyl groups. For a molecule that small with so many polar hydroxyl groups, they're highly soluble, which is good because then they can easily be transported around our body through bloodstreams. Now, alpha glucose and beta glucose, they are 2 isomers of glucose molecule. And what they do is that they differ by the position of hydroxyl groups on the first carbon. Again, we said glucose, galactose are isomers, but glucose itself also has different isomers. Okay? So you have hydroxyl groups facing down, that's alpha glucose, and facing up, that's beta glucose. Okay? So they are optical isomers because they differ by the position of that groups on the same chiral carbon. Okay. So alpha glucose is the monomer of starch and glycogen. These are the 2 polysaccharides that can be broken down and used by our body. Okay. Our body would prefer glycogen because it's easier to use, but we can also process starch. Then beta glucose makes up a cellulose molecule, which is the major cell unit in plants, but unfortunately we cannot use beta glucose, so our body cannot utilize cellulose to actually for energy. Not that it doesn't store energy, we just can't use it. Right. So disaccharides, When different monosaccharides come together, they can go through a condensation reaction where the hydroxyl groups on both molecules will condense and let go of one molecule of water. What the result of that is a ether link. So basically now, once they go through a condensation reaction, they're connected by one oxygen atom, and that is a ether link. Or in food chemistry, we also call it glycidic link. Okay? So since it's a condensation reaction, again, water is produced as a byproduct. So atom economy is not 100%. Polysaccharides. So disaccharides, if different sugar can form disaccharides, of course, you still have results like the result is that you have two rings connected together, and each rings also have a lot of hydroxyl groups on it. They can go through other condensation reactions with another molecule. So the chain just goes on and on and on, right? So condensation reaction can happen between many monomers, many monosaccharides, and as a result, polysaccharide is produced. The fundamental differing quality is that polysaccharides are generally insoluble. So as a result, they need to be broken down to be transported. So whenever you have a bite on a bread, then you're actually eating polysaccharides. And what your body does is that it actually breaks it down first into monosaccharides so that it can be transported through your blood. And then once it goes into a particular part of the body, let's say your muscles, then your muscle, if the muscle doesn't really need to use that energy stored in that monosaccharide at that moment, then they assemble them again into polysaccharides so that they can be stored in your muscle to be used in future. Okay. So for animals, we normally use glycogen for energy storage. Yeah. And for plants, they use starch or cellulose. Okay. So let's look at amylose. So condensation reaction between alpha glucose on C1 and C4 in particular will create a linear polymer. That is amylose. So starch has two versions. One is strictly linear, that is condensation reaction on C1 and C4 only, and then produces amylose. Sometimes the condensation reaction can happen on different number of carbons, like not necessarily C1 and C4, maybe C1 and C3. As a result, then you produce a lot of branched polymer, and that's what we call amylopectin. Okay. Still alpha glucose, so our body can use it. Okay. Glycogen is a much more branched version of alpha glucose polymers. So starting from amylose, not branched at all, amylopectin, a little bit branched, and for glycogen, very, very branched. Okay? So glycogen is normally used by animals to store energy. It has many branched ends, which makes it easier to break down to be used, because all these branched ends allows enzymes to access easily. Right? As a result, energy can be readily obtained in the form of glycogen. Plants, on the other hand, they just use starch to store energy. Okay. It's not like they have to do a 100-meter sprint right away, so they need to use energy very quick. So they don't really need glycogen. But we humans, we need to move fast, so we need to use glycogen. Right. Cellulose. Cellulose is the straight-chain polymer of beta-glucose. And beta-glucose, because of that optical isomerism, so our body cannot recognize beta-glucose. We don't have the necessary enzymes that fit onto beta-glucose. As a result, we can't really use beta-glucose to obtain energy. That's a difference. So you can see that a little bit difference, like even just the position of the hydroxyl group on the same carbon creates that optical isomer that makes a fundamental difference as to whether our body can recognize it and use it or not. Right? So As reaction needs to occur for beta glucose on C1 and C4 to make that linear straight chain polymer. So every second beta glucose needs to be inverted for good alignment as compared to starch or like glycogen, right? So starch doesn't have to be inverted. They all have that side chain, that extra CH2OH group on top, right, on the same direction. But for cellulose, they have to be alternating top, bottom for good alignment. Okay? So cellulose is most abundant molecule in living tissue. Right. Here is a list of many important carbohydrates. You don't really need to memorize these, but being familiar with these compositions will be good, especially for the last polysaccharides, the 3 polysaccharides. It will be really helpful if we know that glycogen and starch are made of alpha glucose, and cellulose is made from beta glucose, and our human body can utilize alpha glucose but not beta glucose.